In Unit 4 of Specialist Mathematics, one of the key topics that we're going to be covering is calculus, and in particular integration and some advanced integration skills. What you see on the screen at the moment is an excerpt out of the Specialist Math formula book for the calculus section. And I want you to pay particular attention to the bottom three on the left-hand side. So we've been looking at integrals and derivatives of some reasonably simple functions up until now. And what we need to do is expand our understanding and knowledge and our function base. What I want you to notice in the bottom is when we start to integrate, particularly the functions that that have a particular square roots and reciprocal type functions, then when you find the integrals, you actually get what we're going to call a sine to the power of -1 or cos or tan. And they are very typical solutions in calculus. So what we need to do is work out, well, what are those functions and what do they look like and how do they behave before we can actually start to look at derivatives and integrals of functions that involve them. So that's what the focus of today's video about. We're going to be looking at inverse trigonometric functions. Now, in year 11, in unit 1, you were looking at inverse functions. And I just want to recap a little bit about that before we get stuck into these periodic functions. So what you see on the screen is two functions. We've got y equals e to the power of x, and we've got y equals log base e, or ln x. And we know from our explorations that those two functions, exponentials and logs, are inverse functions of each other. They typically undo each other. And we also discovered back in methods and in year 11 that not only are these inverse functions of each other, but they're also reflections. So we have the y equals ln x, for example, the function at the bottom. It is an exact mirror reflection of y equals e dx across the line y equals x. So this line here is the line y equals x. And we learned some techniques in methods on how to find the reciprocal function by simply swapping the x and y values and then rearranging. And we're going to use similar concepts in this particular unit. The second thing that we need to remind ourselves about, what is actually the definition of a function? And we know the simplistic definition of a function is for every x value there's one and only one y value. And so we looked at the ways that we can define functions, and we looked at the ratios of the x to the y values. And we talked about things like 1 to 1, many to 1, 1 to many, and many to many relations. And only the 1 to 1 and the many to 1 are defined to be functions. And so we just wanted to remind you that. Now, what does a 1 to 1 mean? Well, 1 to 1 simply means if I look at the y equals ln x function, for example, if I choose an x value, and I draw a vertical line through that x value, so if I choose x equals 3, for example, then if I draw a vertical line through x equals 3, then that vertical line is going to cross that function once and once only. Okay, and we define that to be a function. Now, if we think about a periodic function, then a sine function, for example, is it also an example of a function? So let's make this a little bigger to make it easier to see. And for the same idea, but this is not, instead of being 1 to 1, this is many to 1. So what that means is that there are many values of x that are the same as, that will give the same y value. Okay, so for example, if we have the value x equals pi on 2, then the y value that we get is 1. But that's not the only place we'll get 1. As you can see, just even on just this limited graph, there's another one. But we still have, for every x individual specific x value, there is only one y value. Okay, so it still is defined to be a function, but it has a different ratio because there are many x values that give the single y, but there's only one y for every x that defines our function. Okay, so what we're going to be doing is using those concepts and ideas to look at the inverse periodic functions. And there are three, as you'd imagine, because there are three main periodic functions: sine, cosine, and tangent. We're not going to be looking at cot, cosec, and sec. They're not part of this course. and we don't really need to, although we can by using them as the reciprocals of 1 on sine, 1 on cos, and 1 on tan, but that's beyond the scope of what we need to examine. So we're only going to be examining sine, cos, and tan. So a couple of things first before we go any further. We need to understand that the inverse of sine is not the same as the reciprocal of sine. Even though those two words are sometimes incorrectly interchanged, inverse and reciprocal are not the same thing. So we talked about reciprocal functions back in Unit 2, back when we graphed reciprocal functions of sine, and we looked at the properties of those, and we introduced asymptotes and all that sort of stuff. We're not going down that path in this particular unit. We might come across them as a complex unfamiliar type question, just to frighten you a little bit. No, just kidding. But we're not going to be discussing them. So just keep in mind that the inverse of y equals sine x is not y equals 1 on sine x. That is a completely different function. Okay, so what is the inverse of sine x? Well, it's got two particular annotations, as you can see. So first of all, the typical reciprocal would look like sine to the -1 of x, and that's just something that you'd be familiar with using your calculator to determine the angle given the ratio in a problem back in middle school, or even in trigonometric problems. But sometimes, because the sine to the -1 can be misinterpreted as the reciprocal, it's quite often given the symbol arc sine. Whoops, arc sine. Okay, and so just be aware that those two terms are the same. So arc sine or sine to -1 of x, okay, are the inverse functions of sine x. Just another clarification. We've talked about the fact that, for example, sine squared x is the same as sine of x all squared. So we've had that before, and that's true. However, sine to the -1 of x is not sine of x to the -1. Okay, so when we have a negative power, though, that rule doesn't necessarily apply, or if it's a power. Okay, but when we have -1, we do not write it as sine x to the power -1. This here, that's reciprocal. This is inverse. So this is an inverse function. This is a reciprocal function. And they are different. Okay, so this is true. This is not true. Not equal to. Okay, so let's have a look at what this graph might look like for this inverse function. So we've got the blue graph there, and we can see that that's our typical sine x function. So if we want to find its inverse, then we draw the line y equals x, as you can see, and then we reflect it, and we get this curve that's going up the page, as we can see there. So that would be the inverse of sine x. Now, the question I have to ask you, is the inverse a function? Hopefully you will identify very quickly that it is not a function. It's a relation, but it's not a function. Okay, we can quickly prove that simply by drawing a vertical line anywhere that crosses the graph. You'll see that the vertical line will touch that graph in more than one place. So by definition, it is not a function. But if we want to define it as a function, then what we can do is limit the domain. Okay, so we're going to limit the domain of the original function. All right, so if we think about the original function, well, there's an infinite number of possible domains we could choose. So mathematicians have chosen one, and the one they typically choose is this section here for the sine curve. So from minus pi on 2 to pi on 2. Okay, so the domain of the sine function will be minus pi on 2 to pi on 2, giving us a range of -1 to 1. Okay, so that's what we have here. So we can redraw the sine function to the left-hand side, and we can see that its domain starts at -2 and goes to, negative pi on 2 and goes to pi on 2, and its range from -1 to 1. So conversely, if we draw in the reciprocal, as we know, the domain and the range swap because we swapped x and y. So what was the domain becomes the range, what was the range becomes the domain. And we get our function, and it is now a function, because we don't have any more than one y value for any particular x value. And so that's what our new reciprocal function is going to look like. Okay, and notice I've said reciprocal, I said reciprocal and I shouldn't have, apologies, inverse function. Okay, it's an inverse function. This graph up here is the inverse relation. So this graph, the y and dx is the inverse relation. Okay, up the graph. If we want it to be an inverse function, we have to limit the domain. And that's what we've got there. And we're going to be looking at inverse functions. Okay, so what we've did is a summary. Okay, the domain of the inverse function, y equals arc sine x, is negative 1, 1, and the range is minus pi and 2 to pi and 2. Okay, a couple of quick things. There are an infinite number of solutions to sine x equals a half, because we discussed it earlier, because we haven't limited the domain. However, when we're talking about the inverse function, x equals sine to the minus 1/2 has one solution because of the limited domain. Okay, this brings us back to recalling the cast rule. Okay, and the cast rule from minus pi and 2 to pi and 2 is obviously this section here. And 1/2 is a positive value, and it's only that value in the first quadrant, in the A quadrant. Therefore, the value of sine minus 1/2 is pi and 6. So not only do we need to remember that, we should also keep in mind our exact triangles. It's pi and 4, those who can't read my messy writing. Okay, so that's this inverse sine function. Okay, so what about cos? Well, the same process, but choosing the same domain, and I'll just do it very quickly. If we choose the same domain, then we see that there's going to be a problem. Okay, well, yeah, there is. And the problem is that within that same domain, we can't identify the inverse cos function as a function. So we change it. Okay, and the area that we choose is from 0 to pi. Okay, so if we look at the inverse cos function from the domain 0 to pi, we get the graph that you can see there on the left. Okay, we find its reciprocal by reflecting it, I said it again, we find its inverse by reflecting it across y equals x. Then we end up with the new function, y equals arc cos x, and we have a domain and range of negative 1 to 1 and from 0 to pi. So that's what our arc cos function looks like. The arc tan function is a little bit different. Once again, we choose a limiting domain. This time we go back to what we did for sine, because it gives us a function when we do the inverse. So we've got minus pi and 2 to pi and 2. We have that as our original, which we're very familiar with. And on the right-hand side, you can see what the inverse function looks like for tan. This time, however, there's a slight difference in the fact that its range is all the real numbers. And we've got asymptotes at minus pi and 2 and pi and 2. Okay, so we're approaching those values but never actually reaching it. So we're going to get closer and closer and closer. So theoretically, the range will be quite